Lighthouse Scientific Education presents a lecture in the Molecules and Compound series. The topic, Ionic Bonding. Material in this lecture relies on understanding of the previous lectures Bonding and Overview, Covalent Bonding, and Valence electrons, Octet rule, and dot structure. Ionic bonding is another very important topic in chemistry. We will begin the lecture with the definition of the ionic bond. We then move into properties of ionic compounds and the role of electronegativity in ionic bonding. From there, we will review the formation of ions from the perspective of electronic configurations and the octet rule. A discussion of polyatomic ions follows. Some effort is given over to determining formula units. These are the ionic compound equivalent of molecular formulas. Getting ionic charge from formula units is also covered. We end with an overview of the ionic solids, focusing on the lattice. Like the covalent bond, the ionic bond is a form of bonding called the chemical bond. These bonds are within a compound, and they are stronger than intermolecular bonds, which are bonds between compounds. As for a definition, an ionic bond results from the attraction of a positive ion and a negative ion. This is referred to as an electrostatic interaction. Table salt, sodium chloride, is an example of an electrostatic interaction. From the perspective of electronegativity, an ionic bond occurs when the difference in electronegativity between the two atoms in the bond is greater than 1.9. Some textbooks have this value at greater than 2.0. More on electronegativity later. Ions that bond together are called a compound. The term molecule is not used with ionic compounds. Compound is the broader term and molecule a more specific term. Think covalent bond. Ionic compounds often form crystals. We will expand on this topic when we cover the lattice. Ionic bonds are often between a nonmetal, which is a negatively charged anion, and a metal, which is a positively charged cation. Referring to the periodic table of elements, we find the nonmetals to the right of that staircase, colored pink here, and the metals occupying the first two columns, the transition metals, and the heavier main group elements. Those are the ones to the left of the staircase. Ion formation for elements of the first two columns is readily apparent with an inspection of their electronic configuration. That will not be the case with the other metals. These are found in lookup tables. As a heads up, some of these metals are known to form more than one type of positive charge. On to properties of ionic compounds. First to the physical properties. Ionic compounds tend to have high melting and boiling points. Sodium chloride liquefies at about 800 degrees Celsius. Water, in contrast, liquefies at 0 degrees Celsius. Most ionic compounds are hard and rough and brittle solids at room temperature. They often form crystals. Sodium chloride forms tiny cubes. Ionic compounds are generally soluble in water. We all know that table salt readily dissolves in water. The electrical properties of ionic compounds are also of interest. Many ionic compounds are good conductors when dissolved in water. That is because an ionic compound dissolves into its constituent ions, thereby forming an electrolyte. Electrolytes are liquids that conduct electricity. This topic is discussed in more detail in the Ions and Isotope lecture. We can approach ionic bonding from several directions. From the definition of ionic bonds, we see that this type of bonding occurs when the difference in electronegativity between the two atoms is greater than 1.9. A demonstration of the calculation of difference in electronegativity will be done using sodium chloride. A deeper review of electronegativity and bond formation is found in the Bonding Overview lecture. We begin this process by going to a copy of the periodic table with electronegativity values and getting the electronegativity for the two atoms in the bond. Sodium, Na, has a value of 0.9. Write that down. Chlorine has a value of 3.0. Write that down. Remember that electronegativity is the measure of how strongly an atom wants shared electrons. Chlorine clearly wants those electrons more, and in fact, it wants them completely. Now, to get the difference in electronegativity, we subtract the two values. Start with the larger one, 3.0, subtract the smaller one, 0.9. For sodium chloride, the difference is 2.1. Note that we use the ion name chloride for the atom chlorine. Naming of ions in ionic compound is covered in the Naming Compounds lecture, but we will use the correct term here since the change is small. The 2.1 value is then taken to the difference in electronegativity bonding scale. It is found to reside inside the ionic bonding realm. Sodium chloride is an ionic compound. Another way to approach ionic bonding is with ion formation through the lens of electronic configuration. We will use a table comparing an atom's electronic configuration to its most common ion's electronic configuration, which we will fill in as we go along. One more point before we proceed. As mentioned earlier, only the metals in the first two columns of the periodic table have a straightforward connection between electronic configuration and ion formation. The formation of ions for transition metals is significantly more complicated and is usually relegated to a lookup table. This table only will include the first two column metals. In that context, what drives ion formation is that ion electronic configurations tend to be the same as that of a noble gas. This is also consistent with the octet rule, which we will get to momentarily. Central to this table is the electronic configuration of the noble gas neon. It ends with 8 valence electrons, 2s2, 2p6. Starting with nonmetals, a look at oxygen shows that its electronic configuration ends in 2p4. If oxygen gains 2 negatively charged electrons, thereby adopting a -2 charge, it will, in effect, be adding electrons to the 2p orbital, making the ion electronic configuration end in 2p6. 2p4 plus 2 equals 2p6, just like neon. The atomic electronic configuration of fluorine ends in 2p5. If fluorine gains 1 electron, thereby adopting a -1 charge, the ionic electronic configuration will also gain 1 electron, and 2p5 will become 2p6. Right, same as neon. Moving to the metals on the other side of neon, sodium has an electronic configuration that ends in 3s1. If sodium loses 1 electron, it will have 1 more positively charged proton than electrons and adopt a +1 charge. Removing the 1 electron from the 3s orbital will leave the 3s as unoccupied and will therefore no longer be considered as part of the electronic configuration. As such, the electronic configuration will now end in 2p6. Yep, a neon-like configuration. A similar argument can be made for magnesium. Its last occupied orbital is 3s. It has 2 electrons. If it loses 2 electrons from its 3s orbital, it will have 2 more protons than electrons, adopt a +2 charge, and have an electronic configuration that doesn't include the 3s orbital. It will have a neon-like configuration. The final element on the table is the most common 3a or column 13 element found in our studies. It is aluminum, and we see that its electronic configuration ends in 3s2, 3p1. It has 3 valence electrons, and if it was to lose all 3, it would adopt a +3 charge. Like sodium and magnesium, it will no longer have electrons in its outer shell. As such, it will have a neon-like electronic configuration. Ions tend to have electronic configurations of noble gases. Before we move, we should also consider the most unique element, hydrogen. It only has one electron. If it loses that electron, it will adopt a positive 1 charge. Since it has no electrons, it will have no electronic configuration. It is in effect just a proton. In ionic compounds, hydrogen is always a +1 cation. We can come to the same conclusion about ion formation using bond formation and the octet rule. We will review the octet rule here, but a more thorough explanation of the octet rule can be found in the valence electron, octet rule, and dot structure lecture. The octet rule says atoms interact with other atoms such that each has 8 valence electrons, like their nearest noble gas. One way to achieve an octet is to gain or lose electrons, forming ions. Consider an atom of sodium, atomic number 11. It has 3 shells to put its 11 electrons in. Electrons are shown as dots in this model. 2 dots go in the first shell. 8 go in the second shell. That's 10 so far. And the 11th and its lone valence electron goes into the third shell. It is placed on the side as opposed to the more common position on the top of the shell for demonstration purposes. And then there is the chlorine atom with its 17 electrons. 2 go in the first shell, 8 going in the second shell, and the remaining 7, all valence electrons, go into the third shell. We can see that the arrangements of valence electrons in the model is similar to the dot structure of the element. That is, 4 orbitals capable of holding a maximum of 2 electrons each. If we were considering the formation of a covalent bond, we would pair a single electron in sodium with the orbital containing a single electron in chlorine. But the huge difference in electronegativities tells us that chlorine is not going to share its electron, and furthermore, it is going to take the electron that sodium would have shared. Sodium now has only 10 electrons, like the noble gas neon, and the chloride has 18 electrons, like the noble gas argon. The sodium ion still has 11 positively charged protons, and will therefore have 1 more proton, then electron, and adopt a positive 1 charge. Furthermore, the empty shell is not considered part of the ion. We saw this when looking at the ion electronic configuration of sodium. As such, the cation will have a smaller radius than its corresponding atom. Chloride, with its 18 electrons, still only has 17 positively charged protons. Therefore, it will have 1 more negative charge than positive charge. So chloride adopts a net negative charge. And since 17 protons cannot be expected to hold 18 electrons as tightly as it held 17, the radius of the chloride ion is greater, leading to the rule that the anion will have a larger radius than its corresponding atom. Now to bonding. And to emphasize that ionic bonding does not have orbital overlap like covalent bonding does, a pair of artificial barriers in the form of parentheses will be put around the ions. Ionic bonding is a charge-charge interaction. Positive charge is attracted to negative charge. Negative charge is attracted to positive charge. This is an example of an electrostatic interaction. Such interactions are the result of attractive or repulsive forces between atoms, ions, or compounds. What we are doing here is giving a name to the attraction of positive and negative charge, as well as the repulsion of positive-positive or negative and negative charge. The ionic bond is an electrostatic interaction, attraction in this case. There is an analogy to charge-charge interaction that most of us are more familiar with. It is the attraction of magnets. The positive and negative attraction of charges is similar to the attraction of north and south poles of the magnet. When the north and south poles are brought together, they attract each other, just like the positive and negative charges do. And just like the electrical attraction, there is no overlap of matter. That is, the magnets come together, but they're just touching. We are contrasting with the orbital overlap found with covalent bonding. Another similarity is that both electrostatic and magnetic attractions require energy to separate. And pulling apart attracted pieces is exactly what we are going to talk about in our next topic, the solubility of ionic compounds. We will limit our discussion of solubility to ionic compounds dissolving in water. In that context, water will be providing the energy to pull the ions apart. First, to a definition of solubility. Solubility is the property of one substance, referred to as the solute, which is the ion compound, to dissolve homogeneously in another, referred to as the solvent, and that will be the water. Solubility will depend on the outcome of competing electrostatic forces. Ionic compounds dissolve in water if the total electrostatic attraction of water for the ions is greater than the attraction between the ions. Bringing back sodium chloride as an example of an ionic compound, we see that the electrostatic attraction between the ions is a force of attraction between positive and negative charge. The strength of the attraction of an ion pair is dependent on factors such as the charge on the ions. Larger charge, larger attraction, and the size on the ions. Smaller ions can get closer, and that too means greater attraction. As for the electrostatic attraction of water for ions, well, it's a bit more involved. To show that, we first have to discuss what we mean by dissolved. For an ionic compound, dissolved means the ions are separated to a degree that the ionic bond is broken. We know that breaking a bond takes energy. So where does that energy come from? The solvent water. In the covalent bond lecture, we saw that the hydrogen-oxygen bond is polar. In a water molecule, the oxygen has a partially negative charge, and that comes at the expense of the hydrogens, which consequently adopt a partially positive charge. Water is a polar molecule. Polarity is an important topic. If these partial charges seem confusing, revisit the covalent bond lecture. To give some perspective, that partially negative charge is much smaller than the charge on an electron, or in this example, the charge on the chloride. A partial positive charge is much smaller than the charge on a proton, or in this example, the charge on the sodium ion. So how does this water molecule with its tiny fractions of a charge force a separation of ions with much larger charges? Two things: orientation and numbers. It will take many water molecules, and it will require them to adopt an advantageous orientation. Consider this first water molecule around the sodium ion. The water molecule is arranged such that its partial negative oxygen is pointing at the positive sodium ion. Note the positive charge is not located in just one place. There's only one positive charge sign in this drawing, but the whole sodium ion is treated as being positively charged. That is an electrostatic attraction of water for an ion. But since the partial negative charge on the oxygen is so small, to overcome the attraction between ions, there will need to be many such water-ion interactions, and they will need to adopt the proper orientation. And what about the chloride ion? For the chloride, the water molecule will orient themselves such that the partially positive charge on the hydrogen is pointed at the negatively charged chloride ion. Another example of an electrostatic attraction of water for an ion. And like the sodium ion, chloride will interact with many waters oriented in the same manner. In this two-dimensional drawing, each ion is interacting with 4 water molecules. A better representation would be a three-dimensional drawing that would have 6 water molecules for each ion, 2 additional water molecules per ion. That is, a water molecule could have been added directly in front of the drawing of the ions, coming out of the screen. and another water molecule directly behind, going into the screen. 6 waters per ion gives a total of 12 water-ion interactions for 1 sodium chloride. And that is what we will consider as the total electrostatic attraction of water for ions, at least on a first pass. If the total energy of these water-ion interactions is greater than the energy of the ion-ion attraction, then the ionic compound dissolves in water. Such is the case for sodium chloride. Not all ionic compounds completely dissolve in water, but that's a discussion that will need to wait for the topic of saturation. Our next topic is cations that are not from column 1 or 2 on the periodic table. Many of them, not all, are transition metal cations. Unlike column 1 and column 2 metal cations, these elements adopt charges that are not as readily apparent from their electronic configurations. For the most part, there is no octet rule here. The charges on the cations are gotten from a lookup table like this one here, or it is deduced from the interaction of 1 or more anions. More on that later. An interesting feature of these metal ions is that some can readily adopt more than one type of charge. Iron is found as a +2 and as a +3 cation. Any single iron atom, though, can only be one of the 2 charges. As will become relevant when we get around to the naming ionic compounds in the Naming Compounds lecture, there are 2 ways of naming these metal ions. The more popular way is the systematic naming structure, which uses the element name and a Roman numeral to indicate the size of the charge. The other way is the older structure involving the ion's common name, which is based on the Latin root of the element name. Again, both naming structures are covered in detail in the Naming Compound lecture. On to polyatomic ions. This is a topic also covered in the covalent bond lecture. Some covalent molecules have a net charge, and that makes them ions. This occurs, like it does with atoms, when the total number of protons does not equal the total number of electrons. There are too many polyatomic ions to memorize all their names, but most textbooks have a small list of them, like this one, that contain the ions that come up regularly at this level of chemistry. And students generally learn the names by exposure to them in the course of their studies. The naming structure is explored more deeply in the Naming Compound lecture. In this lecture, we are interested in bonding in polyatomic ions. While polyatomic ions are held together by covalent bonds, they can participate in ionic bonding. For example, the base sodium hydroxide, NaOH. An electrostatic attraction occurs between the positively charged sodium ion and the negatively charged hydroxide polyatomic ion. Note that there is no orbital overlap between the 2 charged species. Ionic bonding involving polyatomic ions has all the properties of ionic bonds covered in this lecture, including solubility. Ionic bonded compounds are not found as individual molecules like covalent compounds, but they are found in particular ratios. Ionic compounds are designated by the simplest ratio of its constituent ions that leads to a combined 0 net charge, and that ratio does not necessarily have to be 1:1. This ratio is referred to as a formula unit. It is analogous to the ratio in the molecular formula for covalent bonded molecules. However, it is not found by pushing dot diagrams together. The formula unit can be better understood and can be predicted for a pair of ions by first noting that the overall net charge on the ionic compound is 0. This means the total amount of negative charge equals the total amount of positive charge. That is, the positive charge and the negative charge have the same magnitude or size, even though they have opposite signs. From this equality, we can use the charges on the respective ions as subscripts on the other ion. A couple demonstrations will help explain this last step. We will start with a pair of ions, cations and anions, and use their charges to determine the formula unit. In the formula unit, the charges on the ions are not included. The formula unit will only have element symbols of the ions and the subscript number indicating the ratio of those ions. It will look like a molecular formula. To proceed, we need to know that the calcium forms a +2 cation and bromide a -1 anion. Determining formula units does require a working knowledge of ion types. The second step in our process has us taking the numerical value of the charge of one ion and putting it as the subscript of the other. For example, the 2 in the +2 of calcium will be the subscript for bromide. In our formula unit panel, we add the 2 as a subscript to bromide. We do the same thing with the 1 in the -1 of bromide. It becomes the subscript for calcium. We double check our values by calculating the total positive charge and the total negative charge given this ratio. This is done by taking the subscript for each ion and multiplying it by the charge on that ion. For calcium, it is 1 subscript times +2 charge for a value of +2. In this formula unit, the sum of positive charge is +2. For the bromide, the sum of the negative charge is 2 subscript times -1 charge for a value of -2. Comparing the magnitude or size of the total charge, we have a +2 and a -2. Does that square with our requirement that the total amount of negative charge equals the total amount of positive charge? Yes, it does. The magnitude of the charges on both ions is 2. One final note. As with molecular formula, a subscript value of 1 is implied. So, with a formula unit, the number 1 is not included. CaBr2. On to another example. This one has the +3 aluminum cation and a -2 oxide anion. The formula unit will have the element symbols and the subscript indicating the appropriate ratio. Once again, we are interested in the numerical values of the +3 charge and the -2 charge. We will employ the same mechanism of taking the 3 in the +3 charge and putting it as a subscript on the oxygen symbol in the formula unit panel. Then we will take the numerical value of 2 from the -2 charge and put it as the subscript on the aluminum symbol. Al2O3. Double checking the total positive charge, there is the subscript 2 times the charge +3 for a value of +6. For the negative charge, there is a subscript 3 times a -2 charge for a value of -6. The charges are the same size and our formula unit is correct. We will do one more using the same cation, but this time the anion will be a polyatomic ion. Since the atoms in the sulfate ion, SO4-2, are covalently bonded, we will treat the sulfate as a single entity and put parentheses around the entire SO4. This helps reduce confusion that can come up when a polyatomic ion as a whole has a subscript. The formula unit will be determined in the same way and the parentheses will stay, unless the subscript on the sulfate is a 1. Starting with a numerical value of 3 from the +3 charge, that will go as the subscript on the sulfate ion. We will come back to this arrangement of parentheses and subscripts in a moment. As for the subscript on the aluminum ion, we take the numerical value of 2 from the -2 charge on sulfate and put it by the aluminum symbol. Al2SO4-3. There are some common mistakes made with the formula unit involving polyatomic ions. It is tempting to take the 3 subscript and multiply it by the 4 subscript on the oxygen, giving the oxygen a subscript of 12. The 3 subscript tells us how many sulfate ions there are, and it's not just for oxygen. Another common mistake would be to multiply the 3 by both the implied 1 subscript of the sulfur and the 4 subscript of the oxygen to get S3O12. This is also a misinterpretation because the subscript 3 does not change the molecular formula or ratio of atoms in the polyatomic ion. That is a 1 for sulfur and a 4 for oxygen. S3O12 says that the covalent bonding is between 3 sulfurs and 12 oxygen, and that is just not the case. The subscript 3 only says how many SO4s there are. Calculating the total positive charge, we have subscript 2 times the charge plus 3 equaling 6. And the total negative charge, there is a subscript 3 times the charge minus 2 for a minus 6. Equal magnitude charges and a correct formula unit. There's one other issue that comes up when determining the formula units from ions. If we start with a plus 2 iron ion and a minus 2 sulfide ion and follow the procedure, we will end up with Fe2S2, which is a correct ratio, but according to our definition of formula unit, we want the simplest ratio. 2 to 2 is not the simplest ratio. We can reduce that ratio by dividing both of those 2's by 2, giving a 1 to 1 ratio. Think of it as simplifying a fraction 2 over 2 to 1 over 1. And as we know, we do not include the subscript values of 1, FeS. The only time this type of simplification is needed is for formula units when all subscript values can be divided by a number other than 1. That is the case when all subscript values are even values, like the case here. Just keep an eye out for that. The flip side of finding formula units from the charge on the ion is finding the charge on one of the ions when given the formula unit and the charge on the other ion. It is really just the reverse of the process we just covered. To get ion charge from a formula unit, take advantage of the equality of charge. The total amount of negative charge equals the total amount of positive charge. With that in mind, calculate the total charge from the known ion, that is the subscript times charge, using that value and the concept of equality of charge. Calculate the necessary charge on the unknown ion so that the subscript times charge is the same size as the total charge from the known ion. Let's try it by getting the charge on the metal ion in the ionic compound PbCl2. Pb is lead. Lead can take on more than one size positive charge, so we simply cannot look it up in a table. Chloride, however, should be an ion we are familiar with. Chloride has a known charge of -1. We have to know the charge on one of the ions. Our rule says to determine the total charge due to chloride by taking the subscript 2 and multiplying it by the charge, which is in -1. The total charge due to the chloride is therefore 2 times -1 for a value of -2. To calculate the necessary charge on the lead, we need to multiply its subscript, an implied 1, by its currently unknown charge, such that the total positive charge from the lead ion is a +2. Same magnitude as the total negative charge from the chloride. Looking at the equation, we can deduce the necessary value since 1 times that value gives a +2. That, of course, is a +2. In this compound, lead is a +2 ion. Yes, going from formula unit to charge requires a bit more work, but the principles are the same. We should also do one where we need to find the charge on an anion, and we might as well make it a polyatomic ion. To keep it on the simpler side, we will reuse a previous compound, Al3SO42. In this example, we are expected to be able to determine or remember the charge on the aluminum ion. It happens to be a +3 charge. To calculate the total positive charge, we need to multiply the subscript 2 by the charge on the aluminum ion, +3. 2 times a +3 gives a value of +6. Therefore, the total negative charge must be a -6. To get that, use the subscript of 3 from the sulfate ion and reason what 3 must be multiplied by to get a -6. And that is a -2. The charge on the sulfate is a -2. A peek at a table of polyatomic ions shows us that sulfate, SO4, has a -2 charge. Whether it is going from formula unit to ions or ions to formula units, the key is balancing the total positive charge and negative charge. Additional examples of finding charge from a formula unit are found in the Naming Compounds lecture under the subtopic of ionic compounds. Our last topic is concerned with the structure of ionic solids. Remember, ionic compounds are designated by the simplest ratio of their constituent ions. We call that the formula unit. Sodium chloride has a 1:1 formula unit. Still, ions are charged particles, and ionic attraction occurs in all directions, not just in the direction of the formula unit. The upshot of this is that the formation of the solid occurs when many formula units, or more precisely, unit cells, are repeated over and over to form a lattice of ions. The unit cell may be a single formula unit or some combination of formula units, and it is an involved topic generally not covered in depth at this level of study. So, we will stay with repeated formula units. It is this grouping of repeated formula units that is called the crystal lattice. Lattice is a term that means array or ordered set. Since ion attraction occurs in all directions, we find that in the lattice, each negatively charged ion is surrounded by positive ions. In sodium chloride, each chloride ion is surrounded by 6 sodium ions. This two-dimensional cartoon shows 4 sodium ions. If drawn correctly in 3 dimensions, there would also be a sodium ion right in front and one right behind the green sphere chloride ion. The chloride would be boxed in much the same way as the water molecules box the ions in when we discuss solubility. Conversely, each positive ion is surrounded by negative ions. In sodium chloride, each sodium ion is surrounded by 6 chloride ions. Again, imagine a chloride ion right in front of and right behind the sodium ion. It too is boxed in. The overall shape of the lattice solid is dependent on the ionic makeup. Different ionic compounds have different numbers of ions in their formula units. This leads to different arrangements or different packings of ions, creating different shapes in a crystal lattice. Sodium chloride is a cube-shaped lattice crystal. You can verify this by taking a single grain of salt and upon close inspection, see that it is indeed a tiny cube. Recapping the lecture. Ionic bonds result from an electrostatic attraction of a positive ion, or metal, to a negative ion, a nonmetal. They are referred to as a compound, not a molecule. Bonding is ionic if the difference in electronegativities is greater than 1.9. Ionic compounds tend to have high melting and boiling points. They are generally hard, rough, and brittle solids at room temperature. Ionic compounds are generally soluble in water, forming electrolytes. Electrolytes are good conductors of electricity. Dissolving in water is a form of solubility and will occur if the total electrostatic attraction of water for the ions is greater than the attraction between the ions. Polyatomic ions are covalent molecules that have a net charge. As such, they will participate in ionic bonding like other ions. The definition of formula unit is the simplest ratio of the constituent ions in a compound that leads to a combined 0 net charge. It can be found using the charges on the respective ions as subscripts. a little practice is needed to become comfortable with the process. Conversely, ion charge can be found from the formula unit using a reverse of the process. And finally, in a solid, formula units or unit cells are repeated over and over to form a lattice of ions. The electrostatic attraction of the ions is in all directions. And that completes our lecture. Please practice what you've covered and equip yourself with a firm understanding of ionic bonding.